Okay, thank you. I'll try to be brief here. My job is to summarize the situation in Axion dark matter experiment. Let me give an apology at the outset. That 10 or 15 years ago, when you gave a talk at IDM on Axions, it was the session was a bit like an echo chamber. Now there is so much work going on, so many beautiful results, so much progress being made that to summarize it all is nearly impossible. So I pulled a lot of material from my colleagues in the past few weeks in preparation here, but I fear that I will need to be selective and not everything will be reviewed. I am going to emphasize that aspect which I think is furthest advanced and I know best, which are the sector of dark matter Axion experiments based on the Primakov interaction, looking through the Axion photon coupling, and the microwave cavity search invariance. And as time permits, I will delve into the NMR-based experiments, and if time truly permits, talk about a couple of very, very beautiful non-dark matter experiments, in particular the ALPS 2 photon regeneration experiment and EAXO, if I may, but time will probably not permit. Axions is dark matter. Luca, thank you so much for a very good introduction there, which will make the first part very easy. We have a decent grasp of what we believe to be the local dark matter density in the vicinity of our solar system. And we have, I think, a decent understanding of what the real velocity would be. And that tells us that, that a cold dark matter would be nearly monoenergetic, but spread by the velocity broadening, actually the square of the velocity, so about 1 part in 10 to the 6th. This is important because in the experiments, the microwave cavity experiments and the lumped element variants of those experiments, they aren't looking, unlike WIMP experiments, they are actually looking at the total energy, mass plus the velocity broadening, and therefore one is going to see one is looking for a line which is going to be exceedingly narrow. Up until a few years ago, we believed that our job was somewhat easier and that there was a lower bound of around a microelectron volt due to the overclosure problem that in the vacuum realignment mechanism you would overproduce axions too light. But recently, work of Graham and Guth have now argued compellingly that that bound is in fact does not pertain, and that naturally one can find axions down to a nano-eV or even a PeV and below. So that makes the field, that makes the enterprise richer, but more difficult. And yet there are very, very good experiments which are probing down in that range. The de Broglie wavelength of this is literally the size of a football field, very high density. So the axions and similar light dark matter particles plead to be discovered in a way that exploits their wave-like nature. And that is precisely the insight of Pierre Sakivy, now close to 30 years ago, in his physical review letter, where he reminds us of the Primakov interaction by which in the 1950s, the first precision measurements of the pion lifetime were done by the fact that a pseudoscalar in the presence of a strong magnetic field, a strong electromagnetic field, can convert into a single photon carrying the full energy, a single photon, not two photons. as the electromagnetic field itself, classical field, can be represented as a sea of virtual photons off of which the axion scatters. And this, of course, this process is reversible. Now, that leads to a realization of the experiment as outlined by Sakivy, the microwave cavity dark matter experiment, where there are three elements. There's a very strong magnetic field, a high Q microwave cavity, and then a state-of-the-art preamplifier to look for a signal that would be exceedingly weak, extraordinarily weak. In modern experiments, we're looking for a signal of maybe 10 to the minus 23 to 10 to the minus 24 watts in a narrow line. And we do not have any good knowledge where that is. Just a couple of guidelines here which are important before talking about the experiment. The conversion power goes as a product of a set of terms, the coupling, the density, and the mass, of which we neither have control knowledge, and then things which the experimentalists control, which is the magnetic field and volume, more is better, the Q of the cavity, more is better, and the form factor, which is effectively represents the overlap of the electromagnetic field, the B field, with the mode which is being induced by the conversion. Now, discovery is not simply an issue of power. It really, everything crucially pivots on the Dickey radiometer equation. The signal to noise is the ratio of the power to the noise power, but then by the square root of the integration time divided by the bandwidth. The bandwidth, of course, is given to us by the expected value, width of the axion. Since we have to scan over many, many decades, it's not sensible to spend an inordinate amount of time. One cannot spend an inordinate amount of time at any particular frequency. And some years ago, we realized that the name of the game was going to be noise reduction. And this is, I think, a beautiful story, which I will tell here. The system noise temperature is the sum of the black body spectrum in the microwave cavity plus the amplifier noise. Now, there is a theorem that for a linear amplifier, it's subject to the standard quantum limit. So in fact, a half quantum from the black body noise and a half quantum irreducible noise from the amplifier leads any receiver based on a linear amplifier, standard linear amplifier, where the Boltzmann constant times temperature equals h nu. So that is the standard limit. It's an irreducible floor unless one can cleverly circumvent it. And I'll talk a little bit later on about a squeezed vacuum state receiver, as has recently been implemented by the Advanced LIGO collaboration and has actually published data. And as I'll mention, in fact, we now, for the first time, have actually broken through the quantum barrier and actually done an experiment, dark matter experiment, where similarly we have used a squeezed state receiver. Now, all across the world, the control of an exploitation of the quantum is a big deal. I mean, governments and large corporations are pouring immense amounts of money in it for reasons of economic and national security, science, and so forth. It's become a national mandate in the U.S. All government agencies are investing in this. But quietly, I think we can be proud to say that while people have been talking, we've been doing. Axions for many years have been actually ahead of the curve and really been driving the quantum revolution. First experiments looking for the axion in the late 80s, 1990. Pioneering experiments at Brookhaven in Florida. We're using transistor-based amplifiers where the system noise temperature was at least a factor of 100 greater than the standard quantum limit. The original ADMX, again, used a HEMT amplifier, transistor-based amplifier. Later on, a first demonstration of a Squid, an intrinsically quantum-limited device, but at, unfortunately, a physical temperature too high to actually fully exploit the benefits of the Squid. But then in the past 5 years, I think we've really picked up steam. ADMX in its current location, University of Washington, now with a dilution refrigerator, is now within a factor of 10 of the standard quantum limit. Haystack, our experiment, Yale, Colorado, Berkeley, at Yale, was right from the outset, starting 5 years ago with a Josephson parametric amplifier, intrinsically quantum limited, a factor of 10 higher in frequency, even with a very small volume, was getting down very, very close to the KSVZ Axion. Was within a factor of 2. We've operated within a factor of 2 of the standard quantum limit. And just recently, we have finished a first data run, which is being submitted for publication, where for the first time ever in a dark matter experiment, we've used a squeezed state receiver, which I'll describe, to break through the standard quantum limit and actually take data at a fraction of the standard quantum limit, which allowed us to greatly accelerate the scan rate of the experiment. Let me just go back and reprise a bit of history. John Clark, a professor here at Berkeley, back already 25 years ago, pioneered a new design of Squid, which allowed the Squid not to be used simply as a DC or low frequency device, but to be a gigahertz amplifier, tunable gigahertz amplifier with good gain and near quantum limited performance. And this was, of course, a major breakthrough, which really kept the Axion enterprise moving forward with a future vision for how it would actually get down to the QCD Axion in a realistic way. Let me talk a little bit about the experiment I'm involved with, Haystack. It is a much smaller experiment. It's a sensitive volume, about 1.5 liters is about 1% of the sensitive volume of ADMX. Right from the get-go, it was using a dilution refrigerator and a Josephson parametric amplifier, which are broadly tunable and intrinsically quantum limited. The name of the game in this business is, of course, since you're dealing with a extremely high magnetic field, and one needs this quantum, very exquisitely sensitive quantum device very in close proximity to the cavity, how do you shield the magnetic field such that the thing will operate? It has to be, one really needs to reduce the stray flux in the proximity of the device down to a very, very, very small fraction of a flux quantum. With much work, we developed a strategy by both actively bucking out the stray magnetic field, persistent coils, 2 layers of ammo metal, sort of cryoperm soft steel, superconducting lead sheet and superconducting aluminum sheet, was able to reduce the field down. And I'm going to use my cursor here. You actually see how we tune with a little flux loop, tune the JPAs over about 50% dynamic range. And you see blue dots and red dots interspersed there. You can see that the amplifier doesn't know if the main 9 Tesla field is on or off. So that constitutes success. And then we actually had an experiment that could stably run. Let me talk a little bit about squeezing. This is a very complex topic. Conrad Leonard and his group have been at Colorado, Joint Institute for Laboratory Astrophysics, have been since the beginning the purveyors of our quantum devices, single JPAs, and now more recently 2 JPA squeezers. This noise at the quantum limit is a very complex topic. You have, by the fluctuation dissipation theorem, you have noise associated with the losses in the cavity. You have of course, the black body photons can be reduced down to essentially negligible levels. You have intrinsic losses and noise by the electronic components themselves. And then what one can do, what one has control over, is in fact the Johnson noise, which in any system, in any configuration I've schematized here, is noise which is effectively reflected off the amplifier whenever one measures it. And it turns out that noise can be looked at as a sort of two components, a sine-like and cosine-like component. The operators associated with them do not commute, and therefore the product of those noise components is conserved. If I schematize the noise here as a little red circle, the Josephson and parametric amplifiers can squeeze noise from one quadrature into another at the expense of noise increasing in the other quadrature. If I squeeze from the X, it shows up in the Y. It's an uncertainty principle. Now, if you consider the situation where I squeeze versus not squeeze, and I inject the signal into the cavity, in the magnetic field, the microwave cavity, over a period of time, you get what are effectively little classical forces that of random phase associated with Axion conversion, which builds up that signal. And so you see, after a period of time, after a run, you have built up a little green margin, a little green bumper, representing the fact that the Axion signals show up at different phases, different conversions. If I squeeze first and then amplify in the same quadrature, I end up with a much larger signal to noise than if I don't squeeze and then simply amplify in that quadrature. And in a testbed experiment at the University of Colorado, where they looked at the degree of squeezing of the noise associated with a phase between the squeezing amplifier and the output amplifier, at pi over 2 and 3 pi over 2, they were able to get down 4.5 dB below the unsqueezed situation, just as predicted by modeling. Now, since the noise reflected off the cavity maximizes off resonance, if you can suppress that, that now opens up the possibility that one can use a much wider width of the bandwidth, and that tells one that when one optimizes the problem, one should really overcouple the cavity to make the resonance not very, very narrow, but very, very broad. If you knew where the Axion was, you wouldn't squeeze at all. You would just simply keep the Q at its maximum and situate the frequency right on the mass of the Axion. Since this is a scanning experiment and one needs to take large steps in time, in this case, the optimized strategy is to overcouple the cavity by roughly twice the degree one can squeeze. This is how the experiment is accelerated. And in a little mock-up at Colorado, they were able to demonstrate that with a squeeze state receiver, one could indeed, in a blind test where one injected signals at various frequencies, in the squeeze state configuration, one could get a speed up of more than a factor of 2 with the design of the receiver they have. Now, this was implemented, and we've just finished our first data run with it at Yale. The publication is going in imminently, and with this very small experiment, we're down now at about under 1.4 KSVZ sensitivity. In fact, this marked a factor of 3 speed up with both the squeezing and other little optimizations that were made. It was far from optimized. The next run, I think, is going to get us about another factor of 4, and an ultimate designed squeezed state receiver that the Leonard Group is working on should give us another factor of 10 on that within a factor of within a couple of years. Let me talk a little bit about the search for axions at much lower frequencies. The limitation of the HEPHY microwave experiment is that the conversion volume is itself the resonant cavity. It is the surrogate LC circuit. Therefore, the frequency over which one can look for the axion is intrinsically linked to the scale of that cavity and the bore of the magnet in which it resides. As was realized by Cabrera and Thomas, Pierre Sakhivi, Dave Tanner, and their group years ago, one could effectively separate the resonant components of a microwave circuit from the conversion volume, and by decoupling the resonant circuit from the size of the conversion volume, one could make experiments which would look all the way down in arbitrarily low in frequency, which is now, of course, is something that we need to do with the realization that the old micro EV lower limit to the axion mass was no longer valid. It's a little bit like if you've ever built in your youth a crystal set radio, one could look at the AM band megahertz signals with hundreds of meters of wavelength with a little coil and a capacitor right on top of a cigar box, sort of 20 centimeters on a side. So here is a new collaboration which have come together representing the existing Stanford DM radio collaboration and the existing ABRA, the MIT-centered collaboration, which is to build a very large-scale lumped element experiment. The physical principle ultimately is the same. The magnetic field induces this effective axion current, which then in turn induces an oscillating magnetic field in the center of this toroidal magnet. And then one has, in fact, the lumped parameter LC circuit, which can be tuned. And this then allows one to look for very, very low frequencies in a finite size conversion volume. There are both toroidal and solenoidal renditions of this design. The University of Florida LC group, the thesis of Nicola Cristoso, in fact used a solenoidal geometry with an internal coil to the magnet to affect the same physics. Now, this is not all new. In fact, at MIT already, the ABRA collaboration already a year ago published very beautiful results of it's a technologically very, very interesting experiment where there was this very small toroidal magnet called ABRA 10 centimeters, achieved a 1 Tesla field and was able to set limits already within a factor of a few of the existing cast solar bounds over a range of 3 × 10⁻⁻10 to 8 × 10⁻⁹ EV. They finished another run for which the limits are actually going to be down below the cast limit. That is just beginning to be written up and should be reported sometime this year. Okay, so this is the prospectus for the DM radio search. It will get down to the middle of the QCD band for either of these particular renditions of the KSVZ or DFSC family of models, and actually get down below this the DFSC limit down to about 100 nano EV, and they're flatten out. Okay, let me skip over, since I want to do first the talk about, before passing back to NMR-based experiments, which I'm only going to touch on briefly, talk about an experiment, a sort of German, Spanish, French experiment, MADMAX, that will be centered in DAISY. This is a very beautiful design and a very, very beautiful engineering implementation as well. And the idea is basically the same. And it in fact, a very similar project has gone on for some while at the University of Washington, headed by Gray Ribka, called Orpheus, differing in some ways in the experimental implementation and the physics described in slightly different language, but of course they have to be the same as well. And in this case, what this is an open-ended resonator with a very large number of dielectric disks. These disks, one can design a system by which the spacing can be changed like an accordion, keeping them equally spaced and parallel to a very, very high degree. And in the presence of a strong magnetic field, one can get Axion photon conversion at the interfaces between the dielectric and vacuum. And in fact, there's a resonant enhancement here. There is this parameter beta squared, which somehow plays the role, is effectively what's called a finesse in the case of a closed resonator. In the case of the University of Washington design Orpheus, in fact, it is a closed resonator with a partially transmissive microwave mirror on one end. And the way to think about this is that for very, very high mass axions, the electric field would produce a very small standing wave of very, very short wavelength compared to the size of the magnetic field. The problem is, of course, that what we call the form factor, the integral of that overlap for something that's highly oscillatory would be zero. By putting in the dielectric disks, in the language of Orpheus, where the maxima or minima are in there actually dramatically changes the field profile by which
5 minutes left.
Thank you. A large non-zero integral to that. This is, of course, the same thing that is going on in MADMAX as well. In the case of the open resonator, they are able to look over a quite broad swath of frequency all at the same time. But otherwise, this looks very much like the microwave cavity experiments. It's going like the square of the magnetic field, the coupling constant squared, and something representing a finesse. And again, the signal is very, very small. Now, I don't show you a picture of the existing prototype on the bench that shows how these dielectric slabs are controlled. But there is a prototype going on at CERN using existing large field transverse dipole, the Morpurgo magnet, 1.6 Tesla. This has been written up. And let me just show you here what the ultimate aspiration of the MADMAX experiment is. This would be a prodigious dipole magnet, sort of 9 coils of niobium titanium here, of about 9 Tesla, about 1.3 meters in effective length and meter diameter, designed for this parameter, which is effectively a finesse of about 30,000. Initially, the MADMAX initially would have a system noise temperature of 5 Kelvin, later on going down to 2, and be able to cover substantially the QCD, in the fullness of time, the QCD mass range up into the hundreds of micro EV range. This is a very, very challenging job, but with I think very, very, very beautifully designed implementation. Let me back up now and go to just say a couple of words and then entertain questions on how to going back to the low mass range, how to go from the nano EV or few nano EV range all the way down. And this is the cosmic axion spin precession experiment. There's two renditions of this. There's what is called Casper Electric and Casper Wind. These are basically NMR-based experiments. This is, again, a very large collaboration with the Casper Wind, the focus at the Center of Excellence in Mainz under Dima Budker, and Alex Sushkoff at Boston University, where what's called the Casper Electric implementation is being built up as well, and the prototyping going on. And in a word, in a traditional NMR, one looks for the dipole moment by putting on a magnetic field and then using a sweep coil and then sweeping the frequency to actually see where one all of a sudden will then get the precession and spin reversal as well. In the case of Casper Electric, one is looking for the Axion gluon coupling. There is an electric field there that sets up again this pseudo or this effective Axion magnetic field. And then one is, by changing the main magnetic field, looking for the place where one gets a resonance and then the spin flips. In the case of the Casper Wind, one is looking for the gradient coupling due to a Axion flow there, but that is the nucleon coupling. And in both cases, what one is really looking for is, of course, the modification of the dipole moment. With that, I have come to the end. Let me just make a couple of concluding remarks here. The Axions and ALPS, interestingly, I think in terms of a dark matter candidate, are the one candidate where achieving the requisite sensitivity was the easy part. The hard part has been coming up with concepts, R&D, for viable ways of extending the mass range and then being able to sweep that mass range in an efficient way. And the idea is that the couplings we're looking for are so extraordinarily weak that one really needs resonant experiments to boost the signal. But of course, the trade-off, of course, is that then these need to be tuned in very small steps, which will take years or decades to do. A lot of credit to the federal agencies in the U.S. For their initiatives in quantum sensing and high-energy physics. Axions have led the way here. We've been both a driver and a beneficiary of it. And for the first time, we have one experiment that has broken through the quantum barrier. To my knowledge, only LIGO within the whole sphere of astrophysical and cosmological experiments, only LIGO, I think, is the only other experiment to our knowledge that's actually exploited squeeze states to improve the sensitivity of an experiment like that. I will leave in the up on the web two very exciting non-dark matter Axion experiments, ALPS-2 and the AXO, which are again the very beautiful physics and very beautiful engineering as well going on there, which are coming online, which will get down to an order of magnitude lower bounds than the existing cast, of which I believe there is exciting discovery potential as well. Thanks to our sponsors, the National Science Foundation and the Haystack Simons Foundation. With that, I will take questions.